Tantor Audio, a division of Recorded Books, presents One of 10 Billion Earths, How We Learn About Our Planet's Past and Future from Distant Exoplanets, by Karel Schrijver, narrated by Steve Menasche. Preface. This book is a journey to planets near and far, to explore their habitability, their past, and their future, and in particular, it is about the Earth-like planets, and above all, Earth itself. This is not only a trek through the solar system and some of the exoplanet systems, but also an expedition through what astronomers have learned about them and how they learned it all. For millennia, humans have forged fairly complex societies, with cities full of specialized citizens, from farmers to sailors, from architects to soldiers. As far as our understanding of the heavens was concerned, however, we did not progress much beyond looking at the stars and wondering what they were, including the few wandering stars that were later identified as planets, while still often considering the sky thronged with divine beings and filled with heralds of things to come. Knowledge about the universe increased very slowly, beginning to accelerate in the late medieval Renaissance, the rebirth of inquisitive critical thinking. But it was not until around 1920 that we began to understand what a star really is and how it can shine for so long and so brightly. Because, for that, we needed to develop, among other things, the science of nuclear physics. Disciplines of science initially move slowly, then can accelerate to an astonishing pace as two things happen. First, we see that as the network of observable or understood phenomena grows, through the development of instruments, methodologies, theories, and in recent decades computers, more connections can be made to create additional new insights. The bigger that network is, the faster it can add new links of understanding. Second, a rapidly advancing field attracts new generations of curious scientists with fresh ideas and perspectives, as well as funding to support them. Thus, it came to be that within a few decades from the discovery of radioactivity at the very end of the 19th century, we mostly understood the lives and deaths of all the stars in all their various forms. Another such leap occurred around the transition into the 21st century. It was not until 1995, with the use of newly devised, sensitive instruments, that the very first solid evidence was found of a distant planetary system like our own. Over the following 20 years, we came to know that planets outside the solar system, known as exoplanets, are more common than the stars themselves that they orbit. The story of the solar system and that of other planetary systems illustrates how the science of astrophysics works and why the world around us looks the way it does. This story rests on facts of nature, as scientific stories should, but a long list of facts alone does not make for a good story. So these facts are brought to life by how they were discovered and by what they teach us about the universe. I hope this exploration will reveal to you, as it did to me, some of the beauty and diversity of the universe in which we live, the unfolding story of astrophysical approaches, and the way our imagination pushes back the frontier of knowledge about our planetary system and the billions of others that surround us. Astrophysics, like all physics, is about interpreting what we observe in the context of other things, whether they are occasional similarities or are rules so frequently encountered and tested that they are viewed as laws: gravity, electromagnetism, relativity, quantum mechanics, thermodynamics, etc. The story of our solar system and of other planetary systems is about understanding phenomena based on the combination of all things relevant to that understanding. It is obviously hard to know what is relevant before it is understood, and it is impossible and boring to provide all the facts without any context. I have had to choose what to present when and in what context. But I did want to preserve some of the excitement of the hunt for understanding that all astronomers share. I hope I have found a comprehensible balance. Many of the references in these sections are published in the professional literature written by and for astrophysicists. Often access is restricted to those with library subscriptions or granted only after payment. However, many modern-day authors submit copies of their work to preprint servers where they can be accessed for free, although generally in a form that predates the final editing. The one most commonly used in astrophysics is https://arxiv.org. Where available, the reading list entry includes the link to the archive entry. The astrophysical literature can be searched most readily with the SAO/NASA Astrophysics Data System. http://www.adsabs.harvard.edu, which enables a look through the papers that it references and papers that cite it. As an added benefit, it provides one-click access to any papers that were submitted to the archive preprint server. Chapter 1. From One to Astronomical. Just how many planetary systems exist in the universe, and how these evolve in a bewildering variety of ways, has been uncovered over the course of just 2 decades in surprising leaps forward in the science of extrasolar planets and in the appreciation of how special Earth and its solar system environment are. All this was enabled by the curiosity of a growing population of searching astrophysicists and probing planetary scientists, guided by the modern scientific methods and propelled by rapidly advancing technologies from microelectronics to space travel. This book illustrates key discoveries that teach us about the past and likely future of Earth, and about the habitability or lack thereof of billions upon billions of planets orbiting other stars, which are now known as exoplanets. The account of planetary systems told in the following chapters leads from unhurried, cloaked formation to ultimate brilliant if not cataclysmic demise. Stars are born in batches in dense hatcheries, then leave their nest for a largely segregated existence as they separate from their siblings to move about their galaxy. Eventually, they expire in puffs or blasts, ejecting newly created elements to partake in another cycle of celestial birth and death. Throughout their existence, most stars do maintain company. Many are born with one or more stellar sisters, and most have at least one full-sized planet orbiting them, along with swarms of smaller heavenly bodies with sizes like entire continents down to pebbles and grains of dust. Planetary systems change over time, with phases in which planets resettle closer to or further away from their central star. In doing so, they subject their fellow planets to bombardments by asteroids, if not catastrophically shepherd them into their star or expel them into interstellar space, along the way causing planetary collisions and supplying or removing atmospheric gases and water. Planetary habitability comes and goes with the aging of the central star, with the changes in the magma motions inside the planet, and, at least on Earth, the only world for which we know unambiguously that life exists, with the evolution of life on its surface. Galaxies, stars, planets, and more. The observable universe may contain of order 2 trillion galaxies. That is a number with 12 zeros. 2 trillion galaxies. Each of these contains at least 1 million stars. But many, like our own Milky Way galaxy, or just galaxy for short, contain over 100 billion stars, and some as many as 100 trillion stars. Until just a decade ago, we did not know that it is likely that most of these stars have a planetary system, typically with multiple planets. Each planetary system is thought to have roughly 100,000 objects somewhere in its vicinity that are larger than 100 kilometers, or 60 miles, in diameter. Combining these numbers, there must be, very roughly, 10 octillion large clumps of some mixture of gas, ice, rock, and metal in the visible universe, moving in and between 100 sextillion planetary systems. There could be 10 or 100 times more or less than that. But whatever the numbers turn out to be, there are many large objects floating about in the universe, without even including the multitudes of smaller objects, all the way down to particles of dust and loose fragments of atoms. Earth is estimated to be one of several billion Earth-like planets in the galaxy orbiting within a distance from their stars at which water, if it is present, could exist as a liquid on the planetary surface. Although one of many in terms of size and orbit, Earth remains the only planet that we know to be able to support human life, and in fact, the only one that we know supports any life at all. Whereas for many centuries Earth was, in the human mind, at the center of the universe, it has now attained the status as the sole known hospitable island within reach in the vast archipelago of remote exoplanets that are revealing to us why our world is the way it is. All these galaxies, with their stars and planetary systems, are contained within the part of the universe that we can see, which stretches for 13.8 billion light-years in all directions from Earth. We know of no reason to assume that the universe stops there, or in fact, that it stops anywhere. We just cannot see any further than that, because no light from beyond that distance has been able to reach Earth since the beginning of time. These are all large numbers. Astrophysicists are used to working with such numbers. They are trained to compare such large numbers to other large numbers in order to deduce something about the universe. As an astrophysicist, I can write down these estimates about what surrounds the Earth and the galaxy and beyond, but I cannot grasp their meaning with any correspondence to reality. People just cannot visualize what numbers that large mean, but we can work with them as computational results of the combination of observations with logical arguments. Although we cannot visualize the overall contents of the universe, these numbers, and the observation that they are based on, do tell us a lot. What is clear from them, for example, is that there are plenty of other planetary systems around to compare to our own. Many are too far away to study in any useful detail. Most are indeed too distant to observe at all. But those that are sufficiently nearby to reveal some detail about themselves, still many thousands, offer a great deal of diversity in their properties, the number and orbits of their planets, the masses and rough chemical makeup of these planets, some of their past and future. The information we take from them helps us understand more about the universe, but also about the formation, lifetime, and demise of our own planetary system, the one we call the solar system. The speed at which we learn about this is as amazing as the number of planetary systems we know of. Most of what we know of planetary systems other than our own was put together within just 2 decades. The first cool star exoplanet in Florence. In the fall of 1995, I was participating in a conference of astrophysicists entitled Cool Stars, Stellar Systems, and the Sun. The meeting was one in a series that was held every second year, alternating somewhere either in Europe or in the USA. That year, we were in Florence, Italy. The conference venue was a rather modern building, but it was just a few minutes' walk north of the medieval city center, full of art treasures and architectural marvels. The speakers at the conference addressed a few hundred colleagues from around the world. They were discussing magnetism of the stars, very much like our own sun, including that of the sun itself. The work that I was presenting there was about the properties of the million-degree outermost atmospheres of stars like the sun caused by the magnetism generated deep inside stars. But this conference had topics ranging from newly discovered tiny deep red stars called brown dwarfs to the largest giant stars, and more. Among the long list of entries on the agenda was a presentation by Dr. Michel Mayor of the Geneva Observatory. He reported on the observation of signatures of a planet orbiting one of those sun-like stars, work done with a graduate student, Didier Queloz, and if it had not been for a fatal car accident early on, it would have also included their colleague Antoine Duquesnoy. This was not just a discovery of one more of something, it was the first of its kind. The presentation was followed by deserved applause, but only mildly more than the typical acknowledgement by the scientific audience at a conference. In hindsight, it is extraordinary how little fanfare there was at what turned out to be, in fact, the beginning of a radical change in how we view our place in the universe. The planetary system that is our home was proven not to be the sole such system. It was interesting that this finding was announced in such a fitting place. Centuries earlier, Florence, then the capital of the Grand Duchy of Tuscany, saw the beginning of the Renaissance in which arts and sciences flourished anew after stalling for many centuries in the intellectual freeze of the Middle Ages. Part of that was the discovery of moons orbiting Jupiter, and the understanding that the other planets do not orbit Earth, but revolve around a sun that itself rotates and displays surface features in the form of sunspots. Mayor's exoplanet discovery was the first of many that, just a few years later, would reveal our solar system to be one of many similar planetary systems. It was fitting that the announcement happened in a city where you can sit in a quiet church in its medieval center, the Basilica di Santa Croce, surrounded by tombs and funerary monuments debossed with some of the best-known names of that earlier Renaissance. Among them is Galileo Galilei, 1564 through 1642, who added fuel to another revolution by advocating the concept launched by Nicholas Copernicus, 1473 through 1543, that the planets orbit the sun rather than the Earth, and that the Earth is one of them, and thus itself also moves as part of the heavens rather than being underneath all that. This earlier insight led humanity to realize that Earth is not the center of the solar system, and, as one then thought, of the universe. It occurred not long after the first successful circumnavigation of the Earth in 1522 showed beyond doubt that it was, as many had already concluded, spherical. That endeavor, by the way, was initiated by Fernand de Magalhaes, 1480 through 1521, but completed by the skeletal remains of his expedition. Magalhaes himself was killed in the Philippines more than a year before 18 surviving members of the original crew of about 240 managed to return to Spain. The more recent exoplanet revolution makes us realize what we might have anticipated but could not take to be true until then. Our solar system is just one of an unimaginable number of similar systems that exist throughout the universe. Until 1995, we knew of one single planetary system associated with a common type of star, namely our own solar system. 2 decades after that, thousands of such systems have been observed. Statistical estimates based upon these observations suggest that most stars in the galaxy have at least one planet. With well over 100 billion stars in the Milky Way galaxy, that makes for a lot of planetary systems in just one galaxy. With billions of similar galaxies within the segment of the universe that we can observe, the number of planetary systems out there is expected to be truly astronomical. Transformation and the principles of uniformity and mediocrity. This transformation in our knowledge about planets in the universe is astonishing, but it was not unexpected. Among the fundamental assumptions that astrophysicists make in their work, two have always guided our thinking. First, we assume that unless there is firm evidence to the contrary, the laws of physics are universal. The same chemical elements are assumed to exist everywhere, and the same laws of quantum physics, electromagnetism, and gravity are taken to apply in all places and at all times, not only where we happen to live. This assumption is referred to as the principle of uniformity. Second, we assume that, again, unless there is firm evidence to the contrary, our place in the universe is not special. Now, of course, Earth is special in the sense that we live on this particular planet that happens to be located within the particular planetary family, which we call the solar system, that revolves around our star, which we call the Sun. But we should not assume it to be special in the sense that it has an extraordinary history, is in a very distinctive place in the universe, is temporarily in a special state in some way, or has any characteristic that is well out of the common range of what surrounds us in the galaxy, and that even the galaxy as a whole would not be particularly unusual in any way. This assumption is referred to as the principle of mediocrity. Unless one or both of these two fundamental assumptions about physical laws and circumstances were invalid, we may conjecture that our solar system is not exceptional, and therefore other planetary systems should be expected to exist. Granted, they need not look identical. In fact, they would likely differ in the number and properties of the constituent bodies, including their central stars and orbiting planets, but quite a few should exist given the billions upon billions of stars around us. And that is why astrophysicists have been looking for what we now call exoplanets for a long time. What we did not know was whether planetary systems would be common, or would form under some set of restrictive particular circumstances that we were not aware of. In other words, we did not know whether we should expect there to be a handful in the galaxy or many billions. The expected number makes quite a difference to how many scientists would be willing to invest their careers in the hunt for extrasolar planetary systems. The answer also makes a big difference in how much funding governments, industry, or private donors would make available to pursue the hunt. Although our minds were prepared to find other planetary systems, our technology was not able to pull it off for most of civilization's history. Planets, including those as large as Jupiter, are small compared to the stars that they orbit. Moreover, they are very, very faint compared to stars, because they themselves do not emit light other than the generally feeble infrared glow associated with their atmospheric or surface temperature. Most of their brightness comes from the reflection of part of the tiny fraction of the light from their neighboring star, or stars, that hits the planet. And any star around which they might orbit is very, very far away from Earth, so that seeing a much fainter object right next to them is not technologically feasible in almost all cases for traditional imaging optical telescopes. Each of these aspects makes it a challenge to spot planets outside the solar system. It takes very particular types of measurements, which we will get to later on, with very sensitive instruments and patient, repeated observations of many stars before planets outside our own planetary system can be detected. But astrophysicists have a lot of imagination, and engineers working with them take pride in their innovation skills. All of them are tenacious in getting to their goals. So, in 1995, technology crossed the threshold at which a new field of science became possible: the study of planets orbiting ordinary stars other than our Sun. Once one such exoplanet was found, astrophysicists knew what to look for. As a result, within just a few years of the first discovery, dozens of other detections were reported. The push for yet more suitable and sensitive techniques that followed these first discoveries led to dedicated telescopes on the ground and in space. This yielded several thousand known exoplanetary systems within 2 decades of the first sighting. By knowing exactly under what conditions exoplanets could and could not be detected for any of the methods now in use, astrophysicists estimated how many exoplanetary systems should be out there, even if these were, at least for now, undetectable or at least undetected. The result was astounding. Perhaps almost every star has such a system, although statistics allow that only every third star has one. Regardless, that results in more planetary systems than we can visualize. Just imagine, with the naked eye we can see about 9,000 stars. Not all at once, because no matter where we are on Earth, half the sky is hidden. Even those that are in principle visible at any time and place cannot be seen at one glance because our eyes cannot capture the width of the entire night sky. But if we look at the sky on a clear night, well away from city lights, the several thousand stars we see certainly look like a large number. Astrophysicists have put forward solid arguments that for each of these 9,000 stars which the human eye can see, there are very likely more than 10 million others in our galaxy, and that most of those have a planetary system. If we assigned a dozen planetary systems to each person on Earth, there would possibly still be billions of planetary systems left over in the galaxy. We do not yet know how many planets there typically are in exoplanet systems. Perhaps our solar system is not atypical with its 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. But there is a lot more orbiting the Sun than these large spheres. A few dwarf planets, including Pluto, and many asteroids, comets, moons, and more. As we will discuss later on, however, there is more in the exoplanet zoo. There are what are called the rogue planets, or nomads. These are planets that do not orbit any star in particular, but that wander about the galaxy, moving out there either entirely alone or accompanied by their moons, and perhaps ring systems, such as our giant planets have. By some estimates, there may be some 100,000 objects per star that are larger than 100 kilometers, 60 miles, in diameter, floating unbound between the stars, plus many, many smaller objects. Planet detectives. Humankind went from knowing about one planetary system to knowing it was surrounded in all directions by alien worlds in the span of 2 decades. How did that come to be? What do these worlds look like? What are we learning from all this? What does this mean for finding life on other planets? And how do we know what we know? The last question, how do we know what we know, is an important one to tackle. In many ways, we can think of astrophysicists as detectives looking at a crime scene. Everything could be a clue, so every detail deserves attention, and every object, its place, and any trace on it needs to be reviewed as to whether it provides information about the what, how, and why of what occurred in that place before, during, and after the crime. Astrophysicists, like detectives, cannot perform experiments of the kind physicists can in their laboratories. They have to take their clues only from what they observe. Such a forensic science is challenging, particularly if you have seen only a single crime scene, or rather, if you have seen only a single planetary system, as was the case until the last few years of the 20th century. Of course, much can be.
Sample complete. Ready to continue?